All right, hello class. We're about to go over sections 3.1 and 3.2. Now, section 3.1 is pages 272 to 275, and section 3.2 is 281 to 282. Now, with 3.1, we have basically it's problems 1, 3, 5, and 7. So what I'm going to do problems 1 and 5. And then for 3.2, I am going to, because it's 1, 3, 5, and 6, I'm going to do problems 1 and 6 for 3.2. So 3.1, it'll be 1 and 5, and 3.2, it'll be 1 and 6. All right, so let's get this math party started. All right, so problem number 1. It says your neighbor's son will be attending college in the fall, majoring in mathematics. Woo, yay! Okay. All right. On July 1st, he comes to your house looking for summer work to help pay for his college expenses. You are interested in hiring him to do some odd jobs, but you don't have much extra money to pay him. He can start right away and will work all day. July 1st for 2 cents. This gets your attention, but you wonder whether there is a catch. He says that he will work on July 2nd for 4 cents, July 3rd for 8 cents, July 4th for 16 cents, etc. For every day in July. Do you think you should hire him? All right. Now, we have A. Now, A here says to complete the table. All right, so our table only goes from July 1st to July 8th. I just put July. We know it's days in July. So it's 1, 2, 3, 4, 5, 6, 7, and 8. All right. So then we have pay in cents. All right, so the first day supposed to make 2 cents. Second day 4 cents. Third day will be 8 cents because we're doubling each time. So this would be 16, 32, 64, 128, and then 256. Now, it says B. The pay on any given day can be written as a power of 2. Write each pay entry in the output column of the table and part A as a power of 2. So basically, if you do this would be 2 to the first power is basically 2. 2 to the second power is 4. 2 to the third power is 8, and so on. So we'll put 2 is equal to 2 to the first. We'll put 4 is equal to 2 to the second. We'll put 8 is 2 to the third. We'll put 16 is 2 to the fourth. We'll put 32 is 2 to the fifth.
Um,
64. Oh, I'm sorry. Yeah, thank you.
yeah.
Okay, wait a minute. That 5 look like it's 25. So that would be 2 to the fifth. And then 64 is equal to 2 to the sixth. 128 is equal to 2 to the seventh. And 256 is equal to 2 to the eighth power.
Um, Professor, could you share your screen?
Oh, oh, I'm sorry. Let me get that on here. Okay. All right, sorry about that. Okay. So now we have this here, and let me close this off just a little bit. All right, yes. All right, so we have B. Now we go here to C. It says let N represent the number of days worked. Write an equation for the daily pay P of N in cents as a function of n, the number of days worked. Note that the number of days worked is the same as the July date. So it'll be P of n, because they want us to do P, a function of P of n, is equal to, it'll be 2 to the n power, which is basically what we were doing. So it'll be 2 to the n power. Now we go here to D. How much will he earn on July 31st? Be sure to indicate the units of your answer. Was it a good idea to hire him? Explain. Okay, so D, you'll put P of 31, because remember our N is the same as the date in July. So this would be 2 to the 31st power. So we'll put this in our calculator. And it gives us, you notice here it says times 10 to the 9th power, so we have to move this decimal 9 places to the right. So your answer here would be 2 billion, 147,483,648 cents, which is equivalent to, if we're going to write that in dollars, $21,474,836.48. And that's for, doing some odd jobs. So your answer would be no, I could not afford him. Does everyone follow that? All right, let's go to E. It says, is the function linear? Function is not linear. And they said explain. The function is not linear. The average rate of change is not constant. So it is not linear. Now we come here to F. It says, what is the practical domain of the function defined by P of n equals 2 to the n? All right, so basically we look here. The input, which is n, is the July date. So the practical domain is n equals 1 to n equals 31. That would be the practical domain. Be n equals 1 and n equals 31. Well, 2n equals 31, because it's 31 days. It wouldn't be any decimals. It wouldn't be values lower than that. Now G, it says sketch a scatter plot of ordered pairs of the form n p of n from July 1st to July 8th on an appropriately scaled and labeled axis. Now, what I'm going to do here, I'm not going to really graph on this paper because I don't have the graph paper here. But I am going to show you how to do the scales, and then I'm going to show the graph on Desmos. So right here, N is the date in July, so that would be your x-axis. And then your y-axis would be the pay, or the cents. Okay, so now, Down here you have, it looks like you have about 13 tick marks when you look in your textbook. So since the date's in July, we only want to go up to the 8th. We could start at 0 and count by ones until we get to 8, or you could go even further to 13 if you so choose. Now, as far as the pay in cents, when we look at our table well, I guess I could go back here to A. When we look at our table, our pay in cents is the low at 2 cents all the way up to 256 for 8 days. So on the side here, we just need to get past, well, at least up to about 260, maybe 300. So with that being the case, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 tick marks here. So what we could do if we did everything by 30, so that'd be 30, 60, 90, 120, 150, 180, and so on. Because you have the 10 tick marks, I don't here because I have this limited space. So it'll take you up to 300. And then you would just plot the points, starting with day 1. Day 1 would be 2, and so on. So why don't I put that here? So we had that y, or I could just do a table. Let me just do a table. We do a table, we would go 1, 2, 3, 4, 5, 6, 7, 8. And we'll put in the values. We had 2, 4, 8, 16, 32, 64, 128, 256, and that's it. All right, now I want to show this graph a little better here. Okay, you see how this is curving up. Matter of fact, let me change these axes here. Let me go from 0 for x all the way to, let me go to 10. 0 to 10 for x, and then y, I will go from 0 to 300. All right. It doesn't look that much better, but as you can see, it's going to form this curve here. Does everyone follow that? Okay, and that's basically what you end up drawing on your paper as well. All right, so now we come here to H. It says, is the function discrete or continuous? Explain. Okay, the function, now you must know the definition of discrete and continuous, but the function is discrete because the function is not defined for real numbers between 1 and 2, 2 and 3, comma, etc. Now remember how I told you when we were using dates, we're not using decimals or fractions, we're just using the date. So it's discrete because you're not using the numbers in between like 1 and 2, like you wouldn't have 1.5 or you wouldn't have 1.23. It'd just be the 1, 2, or 2 and 3. You know, it wouldn't be anything in between those numbers. That's why it's discrete. Okay, now we come here to I. which is the last problem for number 1. It says, there is an interesting story about the inventor of chess and grains of wheat. Use the internet to look up the wheat and chessboard problem and answer the following question. If a chessboard were to have wheat placed upon each square, such that 1 grain were placed on the first square, 2 on the second, 4 on the third, etc., doubling the number of grains on each subsequent square, how many grains of wheat would be on the last square of the chessboard at the finish? Now, basically, they ask us what would be on the last square. So basically, from what I understand with the chessboard, there's supposed to be 63 places on the chessboard. So it'll be 2 to the 63rd power. Now, if we put this in our calculator, it's going to give us scientific notation. It's going to give us this long number here times 10 to the 18th power. So we'll need to move this decimal 18 places to the right. So it'll be 9, it's at 223, 372, 0369. So that's 369, that's 10. So we would have to add on 8 zeros. And then now we're done. Now, did they ask us to write it out? No, they did not. So we could just leave it like this. Put our little commas in between the values. And just so that you know, this is 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 850. Wait a minute. Oh, ours didn't go up to. It didn't do the 854. It rounded to 9. So it'll be 900 million. Because it actually supposed to be like 854,775,808, but this actually rounded the value on Desmos. So this would be the answer using Desmos. Okay, now, with that being said, that's problem number 1. Did I answer your question for number 1?
Yes, you did. Thank you very much.
Okay, no problem. Okay, next, we have problem number 5 on page 275. All right. With problem 5, it says determine which of the following data sets are linear and which are exponential. For the linear sets, determine the slope. For the exponential sets, determine the growth factor. Okay, so first of all, we have to determine whether or not this is exponential or whether or not this is linear. Now, you have a couple tools at your disposal. You do have your calculator, or you could do it by hand. So, since these graphs, I'm going to write out 5a. So we have x, we have y. So it's -2, 1/9, -1, 1/3, 0, 1, 1, 3, 2, 9, 3, 27, and finally 4, 81. Now we have our table. We want to determine whether or not it's exponential or linear. So listen, since all of these go up by 1, we don't have to worry about the x value. We're going to concentrate strictly on the y value because the x value, they're all going at a constant rate. Okay, so now, with that being said, we look here at the y. We have to ask ourselves, how did we get from 1/9 to 1/3? But listen, this is what I would suggest you do. Instead of dealing with the fraction, since we have 5 regular numbers here, we could determine our factor from these 5 numbers here and see if they work with these 2 values here. So we ask ourselves, first, let's look at this if this was linear. To get from 1 to 3, we would have to add 2. To get from 3 to 9, we would add 6. So we know this is not linear. So linear is off the table. And just to refresh in your memory, linear, you do addition or subtraction. Now, with exponential, you do multiplication or division. So to go from 1 to 3, we're increasing. So what we would do here, we would multiply. 1 times 3 is 3. Then we say, okay, so we're multiplying by 3. 3 times 3 is 9. Work so far. 9 times 3 is 27. And 27 times 3 is 81. So it looks as though multiplying by 3 works. So we're going to test that theory by going here and taking 1/9 and multiplying 3 by it. Now it gives us this decimal, but we know when we push this here, it will give us the fraction. So multiplying this by 3 gave us 1/3, and then 1/3 times 3, we know it would be 3 over 3, which is 1. So this is multiplication by 3, so it's exponential. So we will write down the data is exponential with a growth factor of 3. All right. Now we go here to B. Still do the table. So we have xy, -2, 2, -1, 2.5, 0, 3, 1, 3.5, 2, 4, 3, 4.5, and then finally 4, 5. Now if you look here, the x value is constant. All you're doing is adding 1. So we'll concentrate on the y value. Now remember, I always start out with linear because to me it's easier to add or subtract as opposed to multiplying or dividing. So with that being the case, to go from 2 to 2.5, we're adding 0.5. If we add another 0.5, that'll give us 3. Another 0.5, that'll give us 3.5, and so on. All of these work by adding 0.5. So this is linear. So this data is linear with a slope of 0.5. Now, since we know this is going up by 0.5, and let me just say this here. With slope, I know you're used to seeing y sub 2 minus y sub 1 over x sub 2 minus x sub 1. But it's actually still the change in y divided by the change in x. That's another way of writing slope, or rise over run. The change in y, we already determined y is going up by 0.5. The change in x, if you notice here, x is going up by a positive 1. So the change in y is 0.5, the change in x is 1, so your slope would be 0.5. Okay, now we go here to C. Another quick table. We have -2, 0.75, -1, 1.5, 0.3, 1.6, 3.12. Wait a minute, I skipped something. Oh, it's supposed to be 2.12, not 3.12. 212, 324, and finally 448. Now, if we look at our x values again, they're constant, they're going up by a positive 1. So now we would just concentrate on our y values. First thing again, I would try the linear method. So if you notice, this increases, so that means we would add. So 0.75 to 1.5, that's adding 0.75. But if we add 0.75 to 1.5, it's not going to give us 3. It's going to be 2.25. So linear does not work. So now we do the exponential. We have to do this by multiplication. I will start with these numbers here and then work my way back. To go from 3 to 6, we'll multiply 3 times 2 is 6, then 6 times 2 is 12, 12 times 2 is 24, and 24 times 2 is 48. Now I'll go back here because we're supposed to be multiplying by 2. I take 0.75 times 2, which is 1.5. 1.5 times 2 gives us positive 3. So it works. So basically, this data is exponential with a growth factor of 2. Okay, now that takes care of 3.1. Now we're going to move on to 3.2, which is on page 281 and 282. Now I said I would cover problems 1 and 6. So problem number 1 on page 281. It says complete the following tables. All right, I guess I gotta keep doing these tables. So we had x, then we had h of x is equal to 0.35 to the x. So we had -3, 23.32, -2, 8.16, -1, 2.86, 0, 1, 1, 0.35, 2, 0.1225, and then 3, 0.043. Now, I took the liberty of writing out the answers because you could basically just go right to your calculator and put in these values, -3 for x, -2 for x, -1 for x, and get your answers for the y. So we really didn't need to take an extensive time for that because we actually did that in previous lessons. Now I'm going to draw the table for the next values. So we have x, g of x is equal to 1/5 to the x. Now, I guess I need to show this again. I'll show it because there could be someone that could just not quite remember what we had covered in class as far as on the calculator. So, what we would do, all right. So we have a couple ways we could write this. We could just do a parenthesis, then 1 divided by 5. The arrow, close the parenthesis, and then take this to the -3 power. Okay, so that would give us 125. We could just keep changing the power. So we'll make that to the -2. That'll be 25. The -1, that would be 5. And then we know to the 0 will give us 1. And to the 1, will give us, well, if you didn't know 1/5 was 0.2, you got 0.2, and then we could take it to the second power, and it'd be 0.04, and then finally to the third power, and it'll be 0.008. Okay, now we go here to B. It says sketch graphs of H and G on the following grid. Okay, listen. When they tell you to sketch the graph, they're asking you just to sketch it, not necessarily to do exact points. So you could just basically do a sketch, but I'm going to show this to you on the on basically Desmos. So we know G of X and H of X is really just saying Y. So we could just say Y is equal to 0.35 to the X power. And then we could say here, now that would be your H of X. Let me extend this out here. Okay, this would be our H of X. Now, what I want to do, I'm going to get a table. And I want to put in the values that we had. Let me put in the -3. And then I guess only thing we was missing was -3 and +3. Okay, now on this, they just rounded to at most 3 decimal places. So, all right, so we have our values here. Okay, so if we come here and look at this graph, you notice here that this graph is in green. This would be our H of X. Now we come to our G of X. Now, G of X, we still will put Y is equal to, and then we will have our 1/5 X. We'll take that to the X power. And then we would do the wheel, and we'll do a table. Now, the only thing we're missing here is the +3 and also the -3. And we have all of the points that we had. And if you notice here, this is purple. So if you notice, the H of X is a little bit wider than the G of X is. The G of X is curving more on the inside, and the H of X is curving more so outward on the outside. So that's basically it for that. But just to illustrate it, if I did a table here, okay, this would be like my G of X, and then my H of X, and neither one of them would touch the x-axis. So just to give a little bit of a sketch. All right, now we look here at C. It says use the tables and graphs in parts A and B to complete the following table. All right. Okay, I should have known it was another table. All right, so we have the function. We had a base, which is B. We have the growth or decay factor. We have the x-intercept. We have the y-intercept. We have the horizontal asymptote. And we have the increasing or decreasing. All right, so we had h of x is equal to 0.35 to the x. Then we have g of x, which is equal to 1/5 to the x power. Now our base. Now one thing that we have to look at here is our problem is really y equals ab to the x. So now we want our base here. So we have a and then b is what's taken to the x power. So with that being the case, you notice here with this equation, 0.35 is being taken to the x power. So it'll be 0.35. 1/5 is taken to the x power. So your base b would be 1/5. Now it says growth or decay. When we look at this graph here, we notice it's going down. And then also, whenever the number that's being taken to the x power or the base is less than 1, it is decaying. And both of these are less than 1. The x-intercept, if you notice on the graph, neither one of them hits the x-axis. So your x-intercept should be none. The y-intercept, both of them hit at 0, 1. The horizontal asymptote, that is when y is equal to 0. And then whether it's increasing or decreasing, looking at this from left to right, it's going down. So that means it is decreasing. All right. So that took care of number 1. Now we need to go over here to number 6. Did anyone have a question on problem number 1 before I go to number 6? Okay. Okay, number 6. It says determine the domain and range of each of the following exponential functions. Now you have to look in your book, but I would do a general sketch here. All right, now it says determine the domain and range of each of the following exponential functions. Okay, first of all, if you notice here, both of these have the arrowheads. And if you notice, this is not impairing it on the x-axis. Domain is determined by the x-axis. So right here, this graph here can be any x value. So the domain is all real numbers. And it's the same thing for B. There's no restriction on x here. So the domain is all real numbers. Now we want to do the range. Now the range, the y value, if you notice, this y value never crosses the x-axis. It has all of the values, but it does not cross the x-axis. So that means we know above the x-axis is basically above 0 because 0 is on the x-axis. So this is above the x-axis. So the range is y has to be greater than 0. It can't equal 0 because it never hits the x-axis. So y, or the range, will be greater than 0. Now here, the range. If we look here, we basically have the same thing going here. It does not cross the x-axis, and it goes on forever. So y is greater than 0. So it's interesting that even though one graph is increasing and one is decreasing, the domain and range is still the same. Any questions? Okay, class. Well, we are done for tonight.